Hello, this is going to be a video tutorial of how to run multidimensional item response theory models in R. I'll go over the R code, the output, and also describe some of the models as well. So specifically, I'll go over exploratory, confirmatory, and confirmatory multidimensional IRT models. I'll also go over the bifactor model and also go over differential item functioning, all using the MIRT package. So just to generally describe what are IRT models? These models are used to describe the relationship between responses to an instrument and the latent factor or variable that they're attempting to measure. So it's described as latent because you can't measure it exactly, but what you can do is try and estimate it. So, in past videos, I've covered unidimensional IRT models, which you can think of them as the traditional IRT models. And by unidimensional, I mean they're mainly used for instruments that are used to pretty much measure, are attempting to measure one type of factor, like for example, math or depression. However, there are also instruments that attempt to measure multiple factors. For example, like instead of math test, maybe a test is designed, like instead of math ability, as it generally trying to be measured, maybe the math test is specifically designed to measure addition and also subtraction. And like in this example, this will be two separate factors. So, for these types of tests, it would require, extensions of the more traditional unidimensional IRT models that I've covered in other videos. So what I'll be covering are these multidimensional IRT models that can measure multiple factors at once. So I'll go over an example, and the dataset that I'll be using for this example in the video is the Generic Conspiracist Beliefs Scale. You can find it at openpsychometrics.org. I already downloaded the dataset using this read.csv file. On the site, you can just download it. I downloaded it, and I already loaded it onto my environment, as you can see here. So, and generally, what this is attempting to measure, what this instrument is attempting to measure, is conspiracy theory beliefs, and it's a Polytomous ordinal scale. As you can see here, one being strongly disagree, and all the way up to 5 being strongly agree. So now I'm also going to do some data cleaning. I'm going to just pretty much take only a subset because it gives you a lot of information and only the first 15 items are related to the instrument. In addition, there's one other field that I'd be interested in taking as well. So I want the first 15 items along with the field named gender. However, I'm using the subset function, and I am asking only give me observations where the gender variable is filled out. So I'll run it. And then I'm just simply removing all, because I've looked through the data set and values of 0 are missing, so I'm setting it to NA. Then I'm just eliminating all the NA just to have a clean data set just for this example. The main goal is just to go over the actual, just go over the R code that's used. And I'm using the na.omit function to eliminate everything. And I'm calling it, the name of my data set will be GCBS. And okay. The first type of multidimensional IRT model that I will try to run is a exploratory. Now you could break up multidimensional IRT modeling into exploratory and confirmatory. So with the exploratory models, you would indicate the number, you still indicate the number of factors, and you can also, you would specify the exact number of factors, and you would also specify the model that you're interested in running. So the function is the MIRT function. All I need to do is put in the data set that I'll be using, GCBS. Now I'm only interested in the first 15 items, so that's why I had the comma 1 colon to 15, like 1 colon 15 is 1 to 15 in brackets. And I indicate 1 here because I'm only interested in one factor, and I'm also indicating item type as graded because I want the graded response model because it is a Polytomous scale. Now, so if you're using dichotomous data, it should be ones and zeros, and I believe Polytomous data, 1 to the number of categories you have, in my case 5, it should be 1 to 5, and missing should just be flagged as NA. Now, you don't necessarily, it will recognize if you don't put item type. Item type indicates the type of model, the type of IRT model you want. And it has, I've gone over 1PL and 2PL models and 3PL, but there are plenty of other types of IRT models you can run that this package, this function actually allows you to run. And it actually will recognize that you are interested in a GRM model just simply based, or graded response model, based on the type of responses in the data set. The default would either be, if it's ones and zeros, dichotomous, it'll be 2PL. And I believe it'll be, if it's more than that, it'll automatically run the graded response model. So you don't have to actually include this right here. Now let's actually run the model itself, and let's call it mod1. No, okay, I forgot to, let me actually call the model itself using the MIRT package. I forgot to do that. So let me just run that. I should have included that. Okay. Now, so I already installed it. You can install it with the function install.packages MIRT. Now, but you also need to call it using library, the library function. Now let's run the model again. Hopefully this time will be successful. And all right, so now let's inspect the model. Okay, I used the coefficient or COEF function on mod1 to look at the actual item parameters that for each item. Now, since I indicated for mod1, for now I'm just interested in one factor, meaning unidimensional in this case. So this will be A1 will represent the slope, and the D's will represent the intercept, my intercept parameters. So what you want to see here is, and it's estimated for each one of the items. Generally speaking, for the intercept parameters, it's in reverse from increasing order. So you want to pretty much see it getting progressively less if the scale is progressively increasing, meaning, for example, the scale that I'm using, it is, let's go back just to show you, it's strongly disagree to strongly agree. Strongly, a 5, strongly agree means I have more of that. If a higher endorsement value indicates more of the construct is being possessed. So like in this case, it's conspiracy theory beliefs. And however, it's in reverse here. So you want to see a drop off if you have it scaled in that way and not reverse coded anyway. So that's what you want to see. You can also consider them to be these intercept parameters. They're also called threshold parameters, and you would expect to see k minus 1. So I have 5 categories, so you would expect 4. And their threshold parameters in a way is described what's the threshold to move from category 1 to category 2, and what's the threshold to move from category 2 to category 3. And that's just another way to describe the parameter. So you can also use the summary function to find more information on the model itself. So this just shows the number of factors in the model. And since I indicated for now I just want to look at one factor, and what the summary provides is the factor loadings along with h2, which is also h squared, which is the also known as the communality, and it's the proportion of common variance. It indicates like the degree to which the factors explain the variance for the items, and these are all the items in the instrument. Like I should have mentioned, there are 15 items in the instrument. And also here some additional information, the sum squared loadings and the proportion of variance explained. So this is just the factors in the model. Now let's run a second model using the same MIRT function, but this time let's have two factors, a two-factor model. And notice here I didn't include that additional item type statement because it will recognize that the default is graded if the data are polytomous. So, but this time let's call it mod 2. And let's wait till the model actually converges. It'll take some time. So, and what we'll expect to see is an additional slope parameter when I run this coefficient function, and also two factors this time when I run the summary as well. And it's a bit more complex when you're running these types of models, and it's it just converged just right now. And let's actually take a quick look. So here. So same as before. However, now there's an additional slope parameter that is also included. Now, and like I said, there should be, when you run the summary, it provides the additional loadings onto the second factor, and also the factor correlations between them. And this is just an exploration. So one thing to note, you can adjust the factor rotations. The default is Varimax. You can generally change the rotation method by adding rotate and indicating the specific rotation method that you want to use. A lot of the rotation methods come from this GPA rotation function of package, and that'll also is used by the MIRT package. Now another feature is you can also suppress for the absolute loadings. So I'm suppressing it just so I can only view factor loadings with an absolute value of at least 0.25. So, and I'm just going to run it again, but this time I'm running the summary function again, but I'm adding suppress. So this way it gives you a clearer description of where the items, which particular items are loaded onto what factors. As you can see here, Q3, the loading onto factor 2, and so on, because if not, it's going to be an NA value. Yeah. So, okay. Now, you might want to actually compare the models, right? So you ran these two models, which one is better? And you can do that with the ANOVA function. So use the ANOVA function and add mod and compare the two models that you created. Now, a significant value, it's going to use this likelihood ratio test, and the significant value would indicate that the more complex model, mod 2, shows to be an improvement in fit. So you can actually pretty much use so basically this provides evidence or supports the use of the second more complex model. Now, if let's go over actual confirmatory. Now, this is when you have a stronger idea of the actual factor structure, or which specific items load onto which factor. And to do that, this will be the confirmatory multidimensional IRT model. And to do that, you can just pretty much indicate using F1, F2, the way I'm indicating right here, indicate that F1 and the items that are loaded onto it. Like, for example, F1, 1, 2, and 4. Item 3 is loaded onto factor 2 right here. And this is how you can, it's done pretty much straightforward. And I will name this structure F structure 1, F struct 1. And I will simply now just use it in the model, and I'll call it mod 3. So just by adding the data set and the factor structure that I created. And let's see what it looks like. So for the most part, as it is, but the main thing that I immediately you will expect to see when you actually run the so it converged, and let's look at the results. Yeah, as before, more interestingly, let's look at at least for now, because what it shows here is that the factor loadings onto these specific factors, right? And yeah, so this way, like, if you have some sort of understanding of the instrument beforehand, and which items are tapping into which specific factors that you're intending to measure. Like for the math test example, like this would be addition and subtraction, but here this is just me running an example. I don't really know much about like the instrument itself. I'm just like pretty much using it as example. I just randomly picked these numbers for the most part. No, I actually didn't. These were in the 3, 8, 9, and 13 were what I got from the exploratory model already. So, and this is what, and this is pretty much one model you can run and what it looks like. Now, let's jump to how to run the actual bifactor model, again using the same data set. Now, what is a bifactor model? It's pretty much when we expect all the items to be loaded onto one general factor. However, there might be a cluster of items or a subgroup or subcluster, you can call it, of items onto some other factor. However, but first and foremost, unlike the confirmatory and exploratory, they're not pretty much unlike the confirmatory, it's not where I was looking at two separate factors. For the most part, they could be correlated or not. This, again, it's one factor, one general factor. All items are loaded into one general factor, and a small number, not necessarily small, but a subset of the items are loaded onto some other factors. So if this is the case, then you can pretty much use a different type of, you can describe the structure in a different way. So now I'm calling this new structure fstruct2, or short for factor structure 2. And what this means here, I'm indicating a number for each of the 15 items. And the number 2 indicates that item 1 is loaded onto some second factor, and item 2 is also loaded onto some second factor. However, item 3 is loaded onto some third factor. So as you can see here, it's 2s and 3s for each item. And what this is describing is one general factor. In addition to that, an additional cluster of items loaded onto one subfactor, and in addition to that, basically one general factor and two subfactors. And I'm calling the 2s represent one subfactor, and the 3s represent a different subfactor. So let's actually run it. And basically I just described the factor. Also, now I'm using a different function because it suggests to use this function because it employs a dimension reduction for the EM algorithm that's being used. And so this way it will be able to, generally speaking, to generate the model a lot quicker. So, and I'm right here, I'm using the bifactor function, the same data set again, and fstruct2. And I'm calling this new bifactor model mod 4. So as we wait for the model to converge, as you can tell, like these models, as the structure starts to get more complex, the time it takes to actually generate for the model to converge is different. So this is why they offer this separate package. This separate function within the package. So yeah, and again, I'm like, this is just for demonstration purposes. I normally you might want to have a better sense of the actual instrument itself. Now, so the model is converged. So let's take a quick look at it using it again, and just to confirm. And more interesting is like the summary for now. So as I said, there basically it's showing you the factor loadings for all the items onto this one general factor, and the subfactors S1 and S2, as you can see here, the actual factor loadings, right? Okay, and it's also showing the factor correlations. So now let's actually go over differential item functioning using the MIRT package. Now, what is differential item functioning? It's basically when there is a different discrepancy between the probability a student or an examinee, so anyone taking the actual instrument, the differentiate when there's a discrepancy between the actual responses or likelihood to endorse compared to their overall level with the specific construct being measured. I'm just trying to speak in a very general way because I'm like so used to using for educational tests. like I want to use the words constructs and speak because you might be using data sets like this. So it's basically, to better describe it, it's when there's group differences or bias items, meaning that two examinees that might fall in different groups, they possess the same degree of the actual latent attribute or factor that you're attempting to measure. However, they're responding differently to a specific item for some reason. And if they have the same level in ability or construct, we would expect them to endorse the item very similarly, right? So from that, we can see that it's biased based on this sort of grouping. Now, before I've done a couple of videos already in differential item functioning. However, those were basically focused. The models used were focused on unidimensional or one factor models. Now, and in that case, another way to look at it is I've only been indicating or detecting differential item functioning, but I haven't described why it's happening. Why differential item functioning might be happening, or this discrepancy or bias item between groups may be occurring, maybe because of differences between those groups on some second factor that I did not measure in the model. So like let's consider another famous example. This is like often used in a lot of textbooks or a couple of textbooks I've seen, is the math test of math problems, right? And I'm using word problems, and one of the word problems is using some sort of baseball reference. And let's say you have international versus non-international as your grouping variable, and you're testing students in the United States. The students, the non-international students may not be able to understand a baseball analogy, and even though they possess the same level of math ability as as an as an international student, or I'm sorry, I meant to say an international student versus a non-international student. They have the same level of ability. The actual international student may get the item wrong because of this specific reference to baseball that's being used. Now, if there's like a cluster of items that are also, for some reason, asking about baseball in this math test, then it's testing some other factor, right? It's testing knowledge of baseball along with math ability. And it's basically, the discrepancy can be described as their differences within this second factor in that case, and that's where the bias is coming from. So now the actual way to deal with this is to look for these factors, and you can run the differential item functioning analyses that I went over in a couple of other videos on the cluster of items specific to them. So let's say if you know items are loaded on this one factor and items loaded on some second or third factor, you can run differential item functioning on each cluster of items specific to that factor. And that's one way that's often used in the research literature of how to run differential item functioning when your instrument itself is multidimensional, testing multiple factors. Now, that's just one way to do it. There have been a number of other models proposed dealing with multidimensionality in tests without having to break it up in that sort of way, and attempting to fit the model. So the MIRT package also offers one way in doing this. Now, so in addition, like the other videos that I went over differential item functioning, and I'll put them in the description if you haven't seen them. It's This is going to be a different method. The MIRT function, if you're trying to assess differential item functioning, requires that you set up anchor items. So in this example, let me go over each step so I don't forget any important detail. So the first thing because I want to run differential item functioning, and since my gender, I want to see the discrepancy or detect items functioning differentially between males and females. So, and I left the gender variable in there. However, it likes the function likes actual categories as opposed to numbers. So I have to create a new field that turns the numeric values to categorical. So this way, f is, I'm using the if-else function, gender equal to 2, set it to female. If not, set it to male. Okay. Now for this demonstration, I'm going to run a specific structure. Now, before, I think I didn't use the MIRT model or a MIRT model function. You can also use this to describe the structure as well. That's another feature available. And I'm just going to name this new structure fstruct3. And what it is basically it's a bifactor model where all 15 items are loaded into this one general factor, and about 4 items, these 4 items are loaded onto some other factor. This is the subfactor. So next is to set the anchor items. So I'm going to select 3 items and set them as anchor items. Now, so the function that we first use, it's 2 steps. You use the multi-group function for the differential item functioning, and it will conduct the multi-group IRT analysis, and the identification of the anchor items allow for like a baseline to be established and the subsequent differential item functioning detection. Now, without setting anchor items, the DIF function detection may also pick up differences between the latent factors and not just differential item functioning. The anchor items are used to identify a baseline model and also distribution properties of the latent factors themselves. They're also going to be set to freely be estimated because we don't necessarily expect those distribution properties among of the factors to be identical. Okay, so I also wanted to make a note of this so I didn't forget. So the selection of the anchor items and setting this sort of baseline, the anchor items should be they should be free of DIF themselves first and foremost, or else everything else will fall apart. And when you do the actual differential item functioning analysis, and doing that in itself is a little bit more involved. So in the other differential item function videos, I showed a method that's also an alternative method that's used that doesn't necessarily require the defining of anchor items, and it's using this purification iterative method. And you might be wondering, okay, well, that method is, why not just use that method? Why go through the trouble of identifying these anchor items and creating this baseline, right? Now, it's there has been some research suggesting that the method that does not include creating anchor items or setting anchor items, it may not work for every type of data set. In the article by Kopf, Zelis, and Strobel in 2015, they actually go over methods of how to select your anchor items. One of the easiest methods, well, not easiest, a straightforward method that you can do is if you have some content expert provide you information on, hey, these three items here, or a set of items, I'm to have, strong certainty that these items are free of diff. Um, and but in their article, they actually go in depth in other methods to actually select anchor items. And I hope I mentioned also, and the reason why the other method where anchor items don't are not needed, the other method that I showed, certain data sets. What I mean by certain data sets, one of them being data sets that might show differential item functioning more strongly for one group versus the other. It may not necessarily work as much, but that's pretty much also covered in their article. I just wanted to emphasize that. Just I don't want to go too in depth, but I just wanted to emphasize that so people know that it's not necessarily a trivial step. But so let's get back to the ART code. So the multi-group function, first I will set the data set. This is the factor structure that I identified. Again, it's going to be, I'm setting up the IRT model for the multi-group analysis, and the group variable is going to be gender 2. It should be some categorical variable. And invariance, and again, I'm setting the anchor items for my baseline, and I'm allowing the hyperparameters here to be freely estimated. And I will name this the MG model for my multi-group analysis. And for this one, because the factor structure is pretty complex, because this is representing a bifactor model, it may take a little bit of time to run. So the model converged, and so the next step is to use the diff, the function itself in the MIRT package. That's used to detect the differential item functioning across the slope and intercept parameters that were estimated. The item parameters are freely estimated across the groups, the male and female groups. Now, technically, what's going on is that an equality constraint is placed on the parameters indicated for each of the items one by one, which will, in this case, it will be 8, 9, and 13. If the model is worse under the equality constraints, then differential item functioning is detected. In this example, the likelihood ratio approach is used, but the wald test can also be used if I set wald is equal to true in the below function. Other diff schemes are also available. So here is the diff function itself. I'm taking the multi-group analysis that I ran, and like I mentioned, I'm checking all the item parameters to see to detect diff across these item parameters between the groups. Sorry, those were my dogs barking at the door. Okay, so the next line is the P adjust. This is pretty much, because we're doing a lot of likelihood ratio tests, this is a way to mitigate any issues or control. This is called a multiplicity control, and it's specifically the Benjamini and Hochberg 95 method. And this is optional to include. However, this right over here, items to test, I'm only testing items 8, 9, and 13 because those are the only items where the all the slope there's a slope variable for each because I'm including A2, meaning their second factors. Their all the structure is bifactor. Each item's on one general factor, and indicated 4 items are on this other subfactor, and I already included one of the items in my anchor when I set up this multi-group model. So now I'm just going to be testing the other 3 items for diff, uh, because I'm also including A2 as well, and this seek stat is equal to 0.01. I'm pretty much just setting the p-value to detect significant values to 0.01, just to be more conservative. So now let's let it run, and what it will do is provide all the items among these 3 items that I'm specifically detecting for diff, 8, 9, and 13. It'll indicate which ones have been flagged for diff. Okay, so that took a little bit of time for it to run. All right, so I'll try to remember to edit the. It was basically a little bit of a lengthy time for it to run, but I'll edit it out. But I just wanted to make a note of that, so you can expect it to take some time to run. So the output returned, and all provides a likelihood ratio test and the p-values and the fit indices of the models, and we can look at the specific p-values in this p column right here, and the adjusted our adjusted p-values in this case, for the most part, will be very similar, very close to being similar. So we can see here that based on the p column, we can flag 8 and item 8 and 13 as possessing as being detected for diff. Also, if you're using the adjusted p-value, you can roughly say maybe just item 13, and because this one's only marginally significant based on the cutoff you'd like to use, you might want to just use, you can report all and everything, of course, depending on what task you're trying to do. But yeah, and that's pretty much it. If you have, let me know if you have any questions in the comment section. Also, you can also use there's a group discussion on the MIRT package, and I believe the author of the package, Chalmers, actually responds to a lot of questions that are there. Yeah, I've actually sent questions as well, and it's actually very helpful in getting me to understand the using this specific diff function. So I hope this was useful. Let me know what you think, and in the future, I hope to post videos a little bit more regularly. And thank you.